All right, line L1, we're in learning task number 2, where we're going to determine bonding requirements that we are going to have. Now, we've talked about this illustration before. The fact that under a fault, we're going to have current that's going to get delivered out of our system, outside of the normal path. What's then going to happen is that current is going to have to try to find its way back to the source. It does not want to go to the Earth. The Earth does not just vacuum up electrons. Instead, what it wants to do is it wants to take a path that is going to allow it to go back to the source and complete a circuit like that. And what happens is when we get that circuit, it's going to be a low impedance circuit, which means that we are going to have a high amount of current. And that high amount of current is then going to go and trip the actual circuit breaker over there. That's the long and short of what we are trying to go and have happen. We saw that this path over here, the actual path that goes from Earth all the way up the grounding conductor over here, does not carry a lot of current. So as a result of that, we get away with having this thing as being in number 6. We just looked inside of the previous learning task. But this path that we have over here, our bonding path itself, is going to have to carry all of the fault current back, which means that it's going to have to be a fairly large path in order to be able to carry, large magnitudes of current. Once again, we're usually targeting about a 5 times value for our current. If that were 100 amp over here, that would mean we were looking to go and have a path that should carry about 500 amps. Not for a long time, so it's not going to have to be sized to nearly the same level, but for long enough that this circuit breaker is going to go and react. As a result of that, we have to have large bonding conductors. Let's take a look at what the code itself actually requires. If you go to that section where it talks about bond conductor sizing, it refers you to 10814. It's no longer 10814 inside of your Canadian electrical code. It is now 10614. We'll just go over to that one. And it's going to be the size of a system bonding jumper or bonding conductor. And the first rule of that one, the sub-rule, says that the size of a field-installed bonding jumper shall not be less than that determined in accordance with Table 16. Note that there is no Table 16A or Table 16B anymore. It is just now going to be Table 16 as well. The higher the current rating of our circuit, the higher that we're going to have to go and respond to that inside of there. So if we take a look at our actual Table 16, go over there right now. Table 16 is going to be based upon the ampacities of our circuit. Now, there's going to be a bunch of places inside of this learning task, because it is built off of the old Canadian electrical code and has not yet been updated, where it's going to refer to different looking Table 16. Don't worry about it. I'm going to walk you through the proper way to do it, which is going to be your Table 16, which is all going to be based off of the ampacities of our system, and then we just refer over based on whether it's a wire or a bus. The old Table 16A and 16B, 16A was wires, 16B was buses. We're going to get to the exact same values as what they have inside of this module, but we're going to get to them with our modern tables. They did not change anything, they just changed the way that we access that information. Okay, I want to go and take a look at the top of the left-hand column over here. This section right over there. It says that not exceeding over here, and then it's going to say it's either not exceeding the ampere rating, or setting the overcurrent device, or the allowable ampacity of the largest ungrounded conductor or group of conductors. Note that it is both of these, meaning that if I had 500 amp conductors and a 400 amp overcurrent, I would be looking at the 500 amp conductors, that it would be not exceeding that. You pick the largest off of those. Either it is the cable size, or it is going to be the overcurrent size that's going to be ahead of it. And that's just because the larger the cables, maybe they're upsized to deal with voltage drop or something like that, but the larger the cable is going to be, the more fault current you're going to be carrying along it. All right. Let's go and take a look at 3 different situations where we'll go through those each one by one and how we size our actual bond. So we have been given a system that is going to be a 400 amp, 120, 240 volt single phase system over here. And we're going to be using non-metallic conduit. It could be HDPE, PVC, DB2, RTRC. There's a whole pile of different types of non-metallic ones, so we would not be able to use the conduit itself as the actual bond. So we're going to have to run in a separate bond. There's a couple of different ways that we would calculate it based upon how we're doing our circuit conductors. We're going to start with option A. Option A would be where I'm going to be sticking all 400 amps along a single conductor. In order to go and do that, we would have to go and size our conductor. We'll take those out of table 2. Sorry, table 4, because we're dealing with aluminum over there. And it said it was all going to be 75 degrees, so I would be looking for a conductor out of the 75-degree column that is going to be good for at least 400 amps. And that would take me all the way down here where I would find a 900 MCM. That 900 MCM conductor is going to be rated for 425 amps. So I'm going to use that now in my table 16 to go and select what I have. Now, 425, does it exceed 400? Absolutely. That's the rating of my cable is 425, and this says not exceeding. So therefore, I would have to move up to 500 because 425 is not exceeding 500. So I'm going to go to the 500, then I'm going to go across that chart, and I'm going to take a look. I see that for a aluminum wire that's going to be able to bond that, I would need to go and have a 1/0. We see that inside of here, where we have got that 1/0 bond conductor. My option B is going to be now where we say 900 kc mil is an expensive wire and it's a pain to terminate, stick underneath, lugs and stuff like that. How about if I take that 400 amp and I parallel it and I pull parallel sets into this conduit over here? So we're doing that. We're going to take 400, we're going to parallel it into 2 sets, 2 line 1s, 2 line 2s, 2 neutrals, etc. When I do that, I'm going to go 400 divided by 2 equals 200. And so I say I need to have 200 amp, but then I cannot go and rate it to exactly the same. I do have to go and derate this thing off of my table 5C. Table 5C is going to be where we find out that if we've got multiple conductors, let's just go over there right now, table 4 and through to table 5C, that I have to go and derate them based upon the number of insulated conductors. In this case, I'm going to have 4 insulated conductors because we do not go and count any of my bonds or any of my neutrals that are going to be inside there. So it's going to be a 0.8 rating that I'm going to go and have for each of those. So I'm going to go and carry that one back up into this table over here, my table 4, at a 0.8 rating. In other words, we'll take 200, divide that by 0.8. I'm just pulling out my calculator over here because I forgot to write the number down before I started recording this, but 200 divided by 0.8 gets me to 250. So I'm going to be looking for something that is going to be good for 250 amps, just due to the derating of having multiple conductors. I go down here in my aluminum 75-degree column, and I see that at 350 MCM. It's going to be the size I need. So 350 is good for 250 amps. Once again, I'm going to take that over to my table 16, and inside of table 16, now I got to go down here. Does it exceed 200? Absolutely. My conductors are good for 250. Does it exceed 300? Absolutely. They're good for 250. And so I might want to go and grab this one over here. However, we got to be really careful about that if we're going to go and grab that one over there, because what I'm going to have is I'm going to have an overall circuit conductor that is going to be larger, right? It's not a 350 we're looking at. We're actually looking at 700 kc mil because we got 2 350s in parallel. So we're going to go and find what that equivalence is for a 700. If I take a look at a 700, its current rating is actually 375. So I'm going to take that value back into here. And I'm going to take a look. Is 375 greater than 300? Yeah. Is it greater than 400? No, it's not. So that means that I'm able to use a number 1 copper. So inside of your book, it says, use the 500 to 700 kc mil rule. You're supposed to just replace that with, use the not exceeding 400 inside of there. So we end up with a number 1 aluminum conductor that we are going to go and use inside of there. This is once again going to be lined up with what we had underneath the old system as well. The last one that I'm going to go and have is going to be where I'm going to split it into 2 separate conduits, because this conduit over here, if you would do the conduit fill, we're not doing that right now, but it's a fairly large conduit. It gets expensive, more expensive components, harder to find, etc. So we're not going to go and use that one necessarily. We might break it into 2 smaller conduits where each conduit is going to be carrying half the amperage with half the lines. They have to be the same length and a whole pile of other stuff to do with paralleling conductors. We find those inside of 12108. But we're just going to be looking at the bond size. So we're going to take that 400 amp. Once again, we're going to divide it by 2. So each of my conductors has to be good for 200 amps. Once again, carrying that back into my Canadian electrical code, we're going to table 4, and we're going down the 75-degree column until we find that a 250 is good for at least 200 amps in the 75-degree column. Perfect. So we have got a 205 amp conductor. We will take that to my table 16. Does it exceed 200? You bet. It does exceed 200. It's 205. So we got to move to the next. Does it exceed 300? No, 205 does not. So I see that each individual conductor would have to be a number 2 aluminum inside of there. Once again, this is going to go and correspond with what we had over here. It is all aluminum. It is all 75-degree conductors. It is just a different way of looking it up than what the book had. The old tables were actually preferred. Lots of people don't like these newer tables. And there is rumor that they're going to be changing again in the 2021. The way that we do the lookups, however, what we should see from change to change is not going to be a change in the actual sizing. How they lay the data out and how we access it might change, but we should still come back to, having a number 1 for this size of conductor is number 2 for this, 1/0 like that. There is, following that inside of your binder, a note there that says, normally the CC does not permit parallel, and it talks about this exception. That whole top little part of the paragraph over there is now been struck because that has been changed. They changed 12.108 to the rule would now state circuit conductors. A bond is not considered to be a circuit conductor. It's considered to be a safety, but it should not be conducting current. So that is no longer going to be an applicable sub-rule that's inside there. Don't worry about that one. All right. Let's look at this table over here. In our CMA sizes, we sometimes are going to be paralleling off conductors. Now, we are allowed to parallel any conductors that are going to be 1/0 or larger as we go through. That is still going to be inside of there. However, if we are going to be looking at having 2 parallel 1/0s inside of a conduit, let's say that I have parallel 1/0s inside of a conduit like that, what is my equivalent size? In order to do that, what we would need to do is we don't just double it up. We need to go and actually add the CMA. Now, if you take a look at the CMA for that, 2 1/0s do work out to become roughly a 4/0 over here. It's not going to become that 2/0. The CMA, the circular mill areas, get added. If I had 2 of these in parallel, I would add 2 of these together, which would get me to 211.2 kc mil, or 200 CMA if I take 2 of those, which I would then go and have to follow down this chart till I find something that is going to be larger, which is going to be my 4/0 that I'm going to have over here. It's this really commonly held misconception that, a 2/0 is twice the size of a 1/0, a 3/0 is twice the size of a, 3 times the size of 1/0, 4 is 4 times the size. If we take a look at the circular mill areas, it's actually the 4/0 is double. And the other ones are each just going up by really just about a third. That's about it. Okay, so I would have to, if I were paralleling those inside of a conduit, if these were 1/0s inside of here, I would have to go and use the lookup out of my table 16. That would be a lookup for a 4/0. What they give you for math down below, 4/0, it would be given as 180 amps. And so you'd have to go and use the not exceeding. When you do the not exceeding 200, using a 4/0 AWG of 180 amps, then what you would find is you could use that same number 4. Once again, lines up. The 2015 and 2018 give us the same results. They just give us different methods of getting there. All right. Terminating bonds. Terminating bonds is going to be less critical than terminating the actual ground. The ground used to have those restrictions that it had to be a permanent type of method. And then the bonds were allowed to be done with split bolts and everything like that. Now everything can be done with split bolts, but it does still need to go and stay in the path at all times. There are a bunch of rules about, that anytime I remove equipment, let's say I take a light off of an octagon box, the bonding path has to stay intact. That's why we have to moret the bonds together in the back, and we take a whip off to, our receptacles or to our lights or anything like that. So when we remove it, the bond path stays intact. When we are dealing with panels and services, we also have to go and watch out for our bonding screws. Now, you should be familiar with the bond screw inside of a panel. Bond screw inside of a panel is going to be a large brass, or sometimes it is a painted green screw that you will see inside of there that is going to go through from the neutral over to the can. Other times, it's going to be like some of the illustrations we've seen where it's going to be a little offset bar that is going to go from inside one of my sideways facing neutral lugs down to the can itself. Either way, it should be easily identifiable. What we need to do is anytime we are working with these, systems that have a bond system applied. And all panels, when you buy them, are going to go and have that bond already applied to it. We need to go and arrange these things so that we don't have what's referred to as objectionable current that is going to pass over top of it. They give you a code rule inside of here, CEC 10200. It is now moved to 10500. We'll just go there really quickly. Which states that there just has to be no objectionable passage of current over top of the bonding conductor. So in other words, we should not have any current that's going to be flowing over top of that bond. Going back to this over here, if I leave my bond screw in, there will be current that will go back. Now, we know that our source is going to go and supply power through the transformer. It's going to go through, this is my service box, my main panel. It's going downstream. We're feeding out of that panel. We're going down to a sub panel that's going to be somewhere further downstream. Out of that sub panel, we go through a load. The load is operating correctly, delivers all its current back onto the neutral, and then when it hits the neutral connection inside of there, part of that will now split. Some of it's going to go up the bond pathway, some of it's going to go up the neutral pathway, and then it's going to go and rejoin and go back to the transformer. We don't have a ground fault, we don't have a line-to-line or a phase-to ground fault or anything like that, but what we have is objectionable current that is going to go and be passed over top of there. What we should have done is we should have removed that bond screw at the second panel. Take a look at this. We see that we've got the bond in there. We've got this bond panel, our bond that has been disconnected. A lot of cases, people will disconnect it, leave it in the bottom of the panel. Don't tape it to the side because the tape can, dry out and then fall, and then you get a screw that falls somewhere and makes contact across stuff. But in a lot of cases, people will leave them inside of the panel so that's visual indication for the next worker, whoever comes into there, that, hey, their bond has been removed. Looking at my current path, once again, this is good current. I see that current would be traveling through from my transformer, through my main panel, through my sub panel, out to the load, coming back on the neutral. And over here, it no longer has that option to go up there. It's just going to travel back to the transformer that I'm going to have. This is the correct pathway for current to be following. Me removing that bonding screw does not cause any issue, though, because if I have got a fault off the system, we end up in a situation that looks like that. Once again, we'll just follow this. This is now going to be fault current. It's going to be delivered from my transformer through my main panel, through to my sub panel. I'm going to have the fault. Once again, it is not going to try to go through the earth. Instead, it wants to go and take the path of least resistance, which is going to go and follow that bond path that we have had. Remember, it's got to be a low impedance path. It will hit the bond path, travel back up. It's traveling over cans and conduit and bonding conductors until eventually it gets back to my main panel, where it travels back up the bond screw in the main panel, hits the neutral, and can return to the transformer. We have a complete path for current with very little resistance at this point, which means we will get a bulk amount of amps. That large amount of amps should go and trip out one, if not both, of these breakers over here. This is the proper method that we should have that. Once again, there is going to be a code rule reference right above this drawing over here. It talks about 10.200 sub 2. That rule no longer exists. Instead, there is 10.500. And if you go over to your Appendix B for that one, that hyperlink is not working off of that one. But I can scroll over there. Let's go down until we hit Appendix B. Lots of good stuff in Appendix B, by the way. And, oops, sorry, we're looking for 10.500, not 10.200. No wonder I'm not finding it there. It states, under normal operation, there should be no objectionable current flow in a bonding conductor. But currents in the bonding conductor that are not considered objectionable are those that may occur under normal operation, such as the temporary current resulting from a ground fault. So if we do have a fault, like what we were shown inside of there, that was a ground fault. In those situations, the bonding conductor is designed to carry the available fault current for the time required to mitigate the faults. And it may carry, the equipotential bonding conductor may carry a portion of the fault current as a parallel fault path. Sometimes, the other components that we have will also go and heat up. But it's not considered to be objectionable because it's during the fault, and we're going to clear that fault itself. All right, going back into this one then. Let's take a look at this drawing over here. Once again, 2015 to 2018, there were changes. One of the big changes that happened inside of the 2015 to the 2018 was that this drawing over here, these services are no longer allowed to be made. Now, they do exist. You will service installations that have them. You don't have to replace them. If they were installed underneath the 2015 Canadian Electrical Code, that's fine. They are still allowed to be that. However, going forward, we're not allowed to do it anymore. And the big thing was that we had these old meter bases where the neutral was bonded to the can itself. Because the neutral was bonded to the can itself, we did not have to worry about bringing a bond back to it. Over here, we would have a PVC conduit with no bond. I'm going to scratch all of that over there, but we would have a PVC conduit with no bond. We could just carry the two hot lines and the actual neutral back through there. The neutral is referred to as a grounded circuit conductor. We'd carry it through there. We would ground that thing down over there. And then this one is just showing, downstream of that, I'm feeding out to another sub panel. I have got a bond conductor that is being placed in. That's going to be that one right over there. That's going across there. That's going to bond that panel. And in this one over here, I've got that bond strap that would go from the neutral to the can. I've got that disconnected inside of here. These days, with the fact that we no longer have got the neutral connected to the actual can, means that we do have to go and have conduits that are going to now have a bond. So if this was going to be PVC, you're still allowed to use it, but I would have to go with a separate bonding conductor and travel through there and attach that to the lug that is going to be inside of my meter base now. It is just a change that has happened. It's actually kind of handy that this drawing is inside here because you will run into the ones that look like this in the field. Don't worry about it. Don't freak out and think that it was done improperly. It was probably just done to a 2015 date of installation rather than a 2018. Okay, bonding conductors themselves and equipment grounds. There is going to be the equipment grounds that we are going to have on our ungrounded circuits, our 3-wire types of circuits that are going to be delta. You'll learn about those inside of third year. Those ones are still going to be required to have an equipment ground conductor, and then the rest of my service is always going to have to be bonded back. Whatever other equipment that I have ultimately ties back to this one over here. We just want to maintain, current flow all the way through it, so it's going to be equipotential. However, it doesn't do anything to go and operate the system. These type of systems, a ungrounded system like this, are going to need to have additional monitoring components. You'll learn about those inside of third year. Particularly, we are going to go and have alarm relays and these fault lights that are going to be continuously watching what's going on inside of it. Last section of the module talks about bonding conductors. Although we talk about conductors and it's usually wire, there are other things that are allowed to go and be our bonding conductors. If you go into your section 10 of the CEC, you're going to find out that we can go and use conductors. They can be insulated or they can be bare. So you can have the green coating over top of them or they could be just bare. We can use bus bars, we can use steel pipe, we can use a rigid metal conduit, unless it's going to be made of stainless steel or subject to corrosion or damage, as well as we are allowed to go and use EMT. Once again, unless subject to corrosion or damage. So EMT in dry locations is going to be fine. EMT that is going to be in wet locations, used outside with weather-tight fittings, or EMT that is going to be placed into concrete slabs that are in contact with the earth or anything else like that. In the Fraser Valley here, in a lot of agricultural buildings, you need to run a bond inside of that. You'll find the rules for those, that additional bonding inside of section 22, which is going to be where we deal with wet and corrosive locations. You'll also find the rest of them inside of section 12, 14 talks about, areas that we have to bond down EMTs.